Every time an athlete does something that seems superhuman, there's this incredible hidden science making it all happen. It's not just pure talent or grit, it's physics, it's engineering, and it's biology, all working together. Seriously, what if I told you the very same principles that keep a skyscraper standing are the ones that perfect a free throw? Let's peel back the curtain and look at the unseen science that really dictates how we move, how we perform, and yeah, even how we get injured.
Okay, I know. It sounds a little bit like the start of a weird joke, right? A pole, a shoe, and a tendon. But the answer to this question, well, it gets right to the very heart of what makes elite performance possible. All three of them are, in their own way, masterpieces of material science. They're either designed by us or evolved by nature to manage just incredible amounts of force. And if you can understand how they work, you're on your way to unlocking your own peak performance.
So, the field that studies all this stuff is called sports biomechanics. And at the end of the day, it's really all about one thing: forces. It's the science of how all these different forces, gravity, the ground pushing back at you, your own muscles firing, how they all affect our bodies and the gear we use. This is the invisible rulebook for everything, from a perfect golf swing to landing a jump without blowing out your knee. Think of it like an invisible coach, constantly giving you feedback on every single move you make. To really get a grip on this, we've got to start with the basics. We need to understand the fundamental forces that are always at play in any sport. I mean, these are the unseen opponents you are constantly battling against, whether you know it or not. Just picture a diver standing at the very end of a diving board. You can see the board bend under their weight, right? That bending is a perfect, really simple example of what we call a load, or a force being applied to a material. But what's actually going on inside that board? Now that's a whole other story. It's a fascinating tug of war. So here's what's so cool. Bending isn't just one single force. It's actually a battle between two opposite forces happening at the exact same time. As that board bends, the top surface is being stretched apart. That's what we call tension. Meanwhile, the bottom surface is being squished together, and that's compression. This invisible tug-of-war is happening all the time, in everything from a swinging bat to the actual bones in your leg when you land from a jump. All right, so we've got these forces, tension and compression, but how different materials respond to those forces? Well, that's what makes a vaulting pole different from, say, a brick. And this is where it gets really, really interesting for sports. So materials basically have two ways of reacting to force. Some are what we call elastic. You can bend them, stretch them, and they snap right back to their original shape. And when they do that, they give back all the energy you put into them. A pole vaulter's pole is the perfect example. Then you have other materials that are plastic. When you deform them, they stay deformed. They absorb that energy instead of returning it. And that is exactly what you want your football helmet to do. That energy we're talking about, the energy that gets stored inside a material when it's bent or squished, has a name: strain energy. And this concept makes the difference crystal clear. A trampoline is designed to be super elastic, right? It gives you back almost all that strain energy as an awesome bounce. A helmet, on the other hand, is designed to be plastic. It absorbs the strain energy from a big impact, so your head doesn't have to. It's literally the difference between a bounce and a thud. Now here's a crucial point. Materials don't always fail in one big catastrophic moment. They can also break down from thousands, or even millions, of smaller repetitive hits. It's called fatigue failure. The classic example is bending a paperclip back and forth. It doesn't break on the first bend, but eventually it just snaps. Why? Because tiny little microcracks form and grow with each bend. And this isn't just for metal. This is the exact science behind most overuse injuries, like the dreaded stress fractures that runners get. Okay, so what happens if we take all these engineering principles and apply them to the most complex and amazing machine on the planet? I'm talking about the human body. Because believe me, your body is an absolute marvel of material science. I mean, we are literally built from high-performance materials. Our bones are the frame, engineered for this incredible strength-to-weight ratio. Our muscles, they're the engines, the things that actually produce all the force. And our tendons, they're the connectors, acting like these super powerful biological springs that store and release energy on command. And just check this out. Take our long bones, like the ones in your legs. They're not solid rods of bone. They're actually hollow cylinders. Why would that be? Well, because engineers have known for a long time that a hollow cylinder is the single most efficient shape there is for resisting both bending and twisting forces, all while saving as much weight as possible. It's a perfect design that nature figured out millions of years ago. But the body has another trick up its sleeve. It's like a secret weapon for generating explosive, incredible power. It's called the stretch shortening cycle.
This is the reason a basketball player dips down before they explode up for a dunk, or why a pitcher has that big windup. It's how our muscles load up to produce way more force than they otherwise could. So how does it work? Well, it's just like a rubber band or a slingshot. Step 1 is the stretch phase. You quickly lengthen the muscle and tendon, like when you dip before a jump. That's pulling the slingshot back. Step 2, all that elastic strain energy gets stored up, mostly in that springy tendon. Then step 3 is the shortening phase. You immediately reverse the movement and jump, and bam, all that stored energy is released, adding this powerful snap to your muscle zone contraction. It's a biological power-up. So once we understand all this, the forces, the materials, the body's mechanics, we can actually start to engineer better results. We can, for all intents and purposes, hack performance and safety. And you don't have to look any further than the shoes on your feet. A modern running shoe is a fantastic example of applied biomechanics. It is not just a piece of foam and fabric, it's a highly sophisticated device tuned to absorb impact, store a little bit of energy, and guide your foot to help prevent injury. Inside that little device, every part has a very specific job. The midsole, that's your main shock absorber, using all kinds of special foams to just eat up those impact forces. The heel counter, that hard plastic cup at the back, provides stability, stopping your foot from rolling around too much. Even the simple insole adds another layer of cushioning. It's a whole symphony of materials working together to protect you. You know, a really common problem for runners is something called overpronation. It's where your foot rolls too far inward after you land, and that can set off this nasty chain reaction of stress that travels right up your leg, leading to shin splints, knee pain, even hip problems. The solution? A well-designed shoe with what we call good rear foot control. That strong heel counter helps guide the foot through a much healthier motion. It's kind of like having a personal trainer for your feet. And hey, it's not just about what we wear on our feet, it's also about what's under them. Modern athletic tracks are engineered surfaces. In fact, the International Amateur Athletics Federation specifies that a track has to reduce the peak impact force by 35 to 50% compared to running on concrete. Let me say that again, 35 to 50%. That is a massive reduction in the repetitive pounding that causes those fatigue injuries we talked about. So look, we've built better shoes, better helmets, and better playing surfaces, all by understanding biomechanics. But the final piece of this puzzle is, of course, the athlete themselves. The real next frontier is using this exact same science to analyze, model, and perfect human movement. Can we find the absolute optimal perfect technique for every single individual that maximizes their performance while making them practically immune to injury? The science says we're getting closer every single day. So what do you think that future of sports is going to look like?